Hello, we are the Rose-Hulman Rover Robotics team. We've been working hard to prepare our rover for the upcoming 2025 competition. Our team leadership is organized into 2 co-captains and 4 sub-team leads with representation from the major disciplines: mechanical, electrical, software, and science. We put great emphasis on collaboration and communication between the subgroups and their leaders. Let's hear from our sub-team leaders about the progress we have made.
We retained the chassis design built last year, which is a robust aluminum tubing frame strong enough to support the weight of electrical components and other subsystems. The wheels are attached via rocker bogies to assist the rover with driving over rough terrain. The internals are shielded with acrylic paneling to provide weatherproofing and to reduce debris impact. The front has a modular mounting system built in to allow efficient switching between the robotic arm and the science package.
This year, we are completely redesigning our 6 degree of freedom robotic arm. The arm features 4 direct drive motors, an offset spherical wrist, and 2 geared down chain and sprocket drive assemblies to increase torque and optimize maneuverability. The end effector can rotate continuously with a slip ring and is driven by 2 high torque servos with customized jagged claws to flip switches, press buttons, lift strange objects, and pick up test tubes. Our team just finished building the arm and are using joint-by-joint control. But we plan on implementing PI control schemes and inverse kinematics to the base 3 joints in the spring.
This year, we've focused on rebuilding our autonomous system with an emphasis on better path planning and obstacle avoidance. We started with making improved basic high-level commands, such as orienting to a given compass heading or driving a set distance forward. Using these basic commands, we then navigate on a path generated based on topological data, which is interrupted and recalculated in the case of unexpected obstacles. Our other main goal this year has been to improve accessibility of our software system to members of the team who are not software developers. This includes getting software systems to run on boot and a user-friendly in-browser control system. This has helped to significantly reduce the reliance on the software team for conducting tests on mechanical, electrical, and science tasks, which has improved the team's pace of development.
The onboard science analysis package mounts to the chassis interchangeably with the arm. A 2-stage elevator lowers the auger to the ground to collect soil onto the rover for analysis. Once on board, the soil is deposited into one of 4 mixing chambers, which are mounted on a shuttle to switch between samples and limit cross-contamination. Each mixing chamber contains a preloaded water and ethanol solution to extract the biomolecules before pumping a small volume of the solution into a cuvette to perform UV absorption spectroscopy. All containers will be fully sealed to prevent leakage, and the solution will be piped through tubing between containers. The spectrometer measures absorption in the range of 200 to 400 nanometers, which allows us to detect the known absorption peaks of biomolecules such as tryptophan and tyrosine at 280 nanometers.